I started. Right. I started the recording. So I will talk about so basically last week we talked about four color theorem, and we talked about the equivalent form in the language of vertex coloring, right? So we talk about dual graphs, and for planar graph we change the graph into its dual graph, and the face coloring problem becomes a vertex coloring problem. There is a corresponding problem called edge colorings. So the definition is similar. Okay, so let me start the definition. A graph G, any graph. So we are going beyond the world of planar graphs. We are talking about any graph now. So any graph. So it is called K edge colorable. Okay. If there is a coloring, so something we call coloring is actually a function. So maybe you already use this notation. So it's from the edge set of G to, for example, K. So you already use this to denote 1, 2, K. This finite set, such that so for any vertex V in V of G, all its incidental edges obtain distinct colors. Okay, so by definition, if I have a triangle, for example, V1, V2, V3, I have to assign color. For example, I put color 1 to this edge, color 2 to this edge, and I have to put another color 3 here. You see? So, for example, 2 colors are not enough to give triangle a proper coloring. Okay? So by this definition, so triangle is 3 edge colorable. But it is not 2 edge colorable. Okay? Is it clear? The definition. So we try to make it slower. So today is not the proof is not very easy. So I make sure everyone knows what's going on here. So we change the point of view. We are trying to give a coloring to the set of edges. Okay, this is an example, right? So, for example, to trying to make some comparison between vertex coloring and edge colorings, let's make another definition which is also very useful. Usually we write a cut of G to denote the chromatic number. So this is actually a notation. So it's a definition for the graph G. So it is so by definition, this is definition. So is the smallest integer K such that G is K vertex colorable. So it means that you can use K colors to give this graph G a proper vertex coloring, and you cannot give a K-1 vertex coloring. Okay, you cannot use K-1 colors to do the same. So this is called a chromatic number. So similarly, we will define something called color prime of G, it is usually referred as chromatic index. So this is for edges of G. So what is that? It is the smallest, the least integer k such that G is k edge colorable. For example, the triangle K3, so it has a, so what is the chromatic number of K3? So what is the chromatic index of K3? The above example tells you that it's 3, okay? And this is also 3, so because they have to be different, they have to be different. So if you color the vertices, you need at least 3 colors. If you color the edges, you also need at least 3 colors. Right? Is it clear?
Yeah.
Great. So let's today our main goal is to prove the following famous theorem. It is called the Wiesen's theorem. It's subtle. It's not like I said. The proof is not long, but it's subtle. There is something we have to be very, very careful. So it says that the chromatic index of any graph G is at most the maximum degree of G plus 1. That's the theorem. It's very beautiful, and let's see why this is beautiful. Okay, so for example, if I take let me make an observation. I claim that the chromatic index of G is actually always greater or equal than the maximum degree. So why is that? Because suppose V is the maximum degree vertex. So it has a degree of V is delta. Delta is this, okay? So delta equals delta of G. You see, already you have to use delta word colors. Is it clear? You see? So locally for this vertex, because this vertex, all these edges share this same vertex. So the degree is delta, degree of V is delta. Then to satisfy the definition, we already have to use delta edges. So after this, we see that the chromatic index of G only 2 possibilities. Either it's delta of G or it's delta of G plus 1. You see, because we have this. So there are, actually there are a classification of graphs. So there are 2 kinds of graphs. Either the chromatic index equals delta of G, or the chromatic index equals delta of G plus 1. Okay. As for a complete characterization, which kind of graph have this and which kind of graph have this, unknown. Okay, it's a complicated question. So you cannot. There is no simple rule to see. Given a graph, you can tell immediately which one is the chromatic index. But it's a very interesting situation. Okay, there are only 2 options. So it makes the problem of chromatic index in some sense extremely simpler than chromatic number. Because if you are satisfied with 2 numbers, that's it. It has to be one of the 2 numbers. But for chromatic number, it's more difficult. Okay. So let's try to prove this Weising theorem. Proof of Weising's theorem. Okay. So induction. But this induction is rather subtle. So let's state the general rule. So we will induct on the number of edges of G. Okay, the number of edges of G. We have to make a claim. So the induction will be we track some base cases. Maybe we track okay, let's see a very simple graph with two vertices. Okay, so this is the G, my G is E2 edge. Okay, so let's say P2 an edge, two vertices, path of length 1, P1. I don't know. Usually some people use P1, some people use P2. Okay, an edge, and the dot of G is 1. Okay, clearly you put one color to it. That's it. So chromatic index of my G is 1. Okay, so it's a smaller than dot plus 1. Dot plus 1 is 2. Okay, so this is a kind of the base case. So after the base case, so this proof is a little strange. We need to recall what's induction. So we prove some cases, and then we look at the next case. So if the induction fails, there must exist some minimal example, minimal counterexample, minimal counterexample, in the sense that, okay, it's a counterexample. It does not satisfy the conclusion, but you take out one edge, it satisfies the conclusion. Okay, so if there is no minimal example, then the induction step always proceed, and you prove everything. So this is a kind of very standard. It's a kind of a very common way to use induction. Okay, maybe when you read the tests, some people say, okay, take a minimal example. In fact, when they do this, they actually is in the part of induction. Okay, is this clear? So we take a minimal example. I think we have seen this in some way, right? This kind of general proof. So if something, you're trying to prove something, if you say if the conclusion is wrong, then you can take a minimal example. Okay, so now we do further. So we change this. So this is a general rule. Okay, take a minimal example. We want to claim that if the conclusion is wrong, so we can find there is this edge xy in the graph. This is an edge, and occurring, which I call C, from EG minus this edge. Okay, which is to dot plus 1. Okay, so using dot So let me write words. A coloring C, which is a proper coloring. So proper coloring is exactly the coloring we allow. Proper coloring C from G minus XY using dot plus 1 colors. So we assume dot equals dot of G, okay, the maximum degree. Okay, but G is not dot plus 1 colorable. So this is just a translation of what I say here. So let's write here 1, or maybe 1. So this is 2. Okay, so there must exist some edge. So take the minimal example, and there must exist some edge. If you take it out, you can actually use dot plus 1 color to color the graph, and the G itself you cannot. Okay, so further, I want to translate this. So what happens is that there exists this edge xy in G. I have a claim. So a proper coloring C from G from EG, okay, proper coloring of G minus XY uses dot plus 1 colors. So all these are fixed. Okay, and then we continue. So if, so this is a long claim. So it's a, let's put a claim start. So for this xy edge, I take it out, and if, right, I look at study, I will study the graph G minus xy. I will draw a lot of pictures. So I look at this graph G, take out the edge xy. So if alpha is a color missed by X, and the beta is a color, so I mean in the color in C, missed by Y in the color in C. So okay, let's look at what is this if. So here, for example, I have this X and this is Y. So this edge has been taken out. Okay, so after you take it out, you see your coloring of all the incidental edges of X, it must miss some color because there are in total dot plus 1 colors to look at, and these edges at most you count. At most they have dot minus 1 edges here. So in C, in this coloring, probably you use 1, 2, 3, 4. X, it must miss some color. Some colors are not used for X. Is this okay? So this is kind of very important. It's a crucial part. So all the arguments later will be centered at this. So I think it's better we pause a little bit to understand this. So this is only if, okay, part. Then the maximum alpha beta paths, okay, starting from Y, must and at x. So this is a kind of long claim. Is it okay? So I'll try to draw a lot of pictures. So this is my vertex x, and here is my vertex y. Originally they have an edge, but now I take it out. So this edge has been taken out. This xy is not an edge in G minus xy, of course. Okay. So, but there might be some paths connecting them. In fact, x in the coloring C, x misses the color alpha. So it means that x does not use the color alpha. And y does not use the color beta. Okay, so but y might use color alpha. So let's see, x does not miss. Let's use the word miss. Misses alpha. Y misses beta. Okay. So if y also, for example, misses alpha, it means that the color alpha is not used for both x and y. So you can put alpha here, and the proof is done. Okay. And you can get a proper coloring of G already. So probably we should not suppose this. So it means that G Y will send some edge here with color alpha. Okay, but X means alpha. The conclusion is that after this, I will look at a path which I call alpha beta path. So this is alpha, this is beta, and this is alpha, then I have beta, and so on. The conclusion is that this path must end here. So, for example, the path end here. So the proof is like the following. So suppose not the proof of the claim. So this proof is very similar to what we have done in the previous lecture, but that was for vertices, but it's very similar. So you see, if the maximal, some maximal path, alpha beta path, starting from y ends at some point, some vertex w. It ends there, meaning that if, for example, I stop here with the color beta, okay, then sort of all other edges, there is no alpha. So this is the only way this path ends here. Otherwise, I can extend this to a longer alpha beta path, right? So it ends here. It means that this vertex here, you cannot extend it anymore. So if this happens, so this is a familiar thing. So we do what? We flip the colors of alpha and the beta for this component containing the vertex y. So we do the following. So let's use red. I change alpha to beta, and I change this to alpha, and I change this to beta, and I change this to alpha. After this changing, you see y. So after this changing. So maybe I obtain the resulting coloring is C prime, for example. Then for C prime, both X and Y miss alpha. Okay, because I changed this to beta here. So Y has no alpha used. So now I can assign color alpha to XY and then thus obtain a proper coloring for T. Okay. And also I didn't introduce any new colors. So the total color, the number I used is at most delta plus 1. Okay, so this is kind of the claim. So the proof is really similar to what we have seen before. So we choose a maximum path and we claim that it must finish, the path must end here. So what must happen is that this has to be continuous and it goes to beta here. Okay, so the alpha beta path must end here. So the alpha beta path starting from Y must end at X. Okay. So we will use this claim a lot during the proof. Any questions? Okay, that's great. So let's digest the claim because this is part of the process. So we need to stop a little bit. So because we will use this, we've used this a lot. So during the proof, there is something Wissing invented. So this is a Wissing theorem. It is called Wissing fan. Wissing's fan. So you see what is going on. So after the claim, we will try to make several steps. Okay, so let me write it. After the claim, we fix an edge which we call XY0. And we take so take it out. So that let's say for the graph T minus XY0, we fix the coloring which exists by induction C0, okay, using at most delta plus 1 colors. Okay, right. So for example, I have X, Y0, and I have this edge taken out. I draw this to denote I'll take out some edge. Okay, right. Okay, so let's say Y0 miss some say Y0 miss some color. Okay. What I want to say is that I want to find an edge y1 such that this edge has this color y0 missed. So this here is a little complicated. Okay. For example, y0 miss a color beta. I want to find an edge x y1 which is assigned with the color beta given by coloring C0. Either I can do it or I cannot. Okay. So I want to do this a lot. So in fact, I would like to find, I want to find a maximum sequence which I call y0, y1, y2 until yk, such that C0 of x, yi for each one, for example, y2, y1, y2, yi, this color is missed by the vertex yi minus 1. So you see, this kind of, I do it for the first step. So if I observe y0 miss some color beta, I'll look for x neighbors which has this beta. If I find it, I put y1 here, okay? And then I ask if y1 miss some color, I still call beta. And I try to look for some y2 such that this edge will have color that y1 misses. So it's not beta because we know that maybe this is beta prime. Okay, so I keep doing this until I cannot continue. Okay, so let me explain. So this is the word. So let me explain. It means what? It means that if yk, for example, the last one, yk miss a color beta, what happens? So for example, I have find this yk here and so on until here is y0, and this is my starting vertex x. So why I say this sequence is maximum? Because if yk miss a color beta, then among all the remaining neighbors, so here is the remaining neighbors of x, which I write R. Among all the remaining neighbors of x, so you have all these edges. These edges, no edge here has color beta. Okay. Otherwise, I'll put this as yk plus 1. Of course, R could be a empty set. So if I exhausted all the neighbors of x, it's also fine. Is it okay? So this is step 1. Let me draw this picture. So let me draw this picture. So this is all the remaining set of x. Okay, so make it better. So here you have yk, and you have to go a long way to define yk. So this is my x, and this guy is y I, for example, and before it you have y I minus 1, and so on. And here in the original graph, we know that we have taken out this edge. So how this thing is called Weaving fan. So it's like a fan. It's like a ventilator, right? It's like a fan, Weaving's fan. Okay. So here this graph is given a coloring which I call C0. So in particular, C0 does not assign color to the edge x, y, 0 because we have taken it out. So there are several properties, right? And C0 of x, y, I here. So here there's a, for example, beta. If C0 give x, y, I, the color beta, it means that the vertex y, I minus 1 misses beta. Okay, so finally, I just repeat this. So if a color alpha is missed by yk, then all edges in xr is not with color alpha, because otherwise it's not maximal. I can define yk plus 1. Is that okay? So it's pretty amazing. This kind of argument eventually it worked out. So it's a very beautiful argument. So this is called a Weaving fan. So the idea is that this is the first step. The idea is that we will manipulate with this kind of Weaving fan with the claim. Okay, remember all the claim says that if you have this x, y, non-edge, the edge you just take it out. If this non-edge, you start with alpha and you consider this alpha beta alternating path. If you start with y and it must end at x, otherwise you can flip the color. Okay, so we have two things at hand. So now we have constructed this Weaving fan. Step 2. Step 2. We want to define new colors, new colorings, and we will move change the graph also. So we define new colors and also change the graph at the same time. So the idea is that, for example, I want to define C1. So how do I define C1? So this is the fun here. I don't care. So this is a yk, and probably here is y1. And originally I have this is a y0. Okay, x y0 is not colored, so it's taken out. So I change this graph to this. So I move this edge to x y0. So what happens is that in my new graph, x y0 has an edge, but x y1 has no edge. Okay, and the remaining part I don't change it. So here is yk, and here is all the remaining vertices. So I change my graph. My graph is that I move this edge with its color together to y0. So this is called a color C1. So C1 is a coloring of g minus xy1 instead of g minus x0. So why I can do this and it's proper? Why I can do this? Because this color beta, it is missed by y0. I put beta here, doesn't matter because y0 has no other edges with this color beta. So I can do this. So this coloring C1 is still a proper coloring. This is a crucial fact. I defined the so-called Weising fan for this. So similarly, I keep moving, okay? For C2, I move this edge with this color, okay? So in fact, I can directly define colorings C1, C2 until CK, okay? And each of them, CI, for example, it move first. It moves, so we move the colored edge. So let's say we move. So how to define CI? We move the colored edge XYI to XYI minus 1. So it means that CI is a proper coloring for G minus XYI. In particular, CK is a proper coloring for G minus XYK. Okay, so for example, this is my YK. And now to draw CK, I have no edge here. And I have all the edges before it because we move it. So here you have Y0. And here is the original remaining vertices. So CK is a proper coloring for this graph for G minus XYK. This is a step 2. Okay, so this process is really like a fan turning, right? So it's called a Weising fan. It's like fan turning. So have a sequence of colorings for a sequence of graphs. Each time I change the graph, actually I take the edge, I move it with the color together to form a new colored graph. So all these graphs are properly colored. Okay, so step 3. Let's look at the final this thing. So suppose YK misses some color beta. Okay, so here in the final graph in CK. Okay, so some questions? Let me check. Is there a question?
On these graphs, only the colors change, right?
Colors doesn't change actually. So okay. Let me see. So the colors the color with edge together they change. Okay. So let me how to explain. So let me say let's look at the very first step. So let me draw C0. C0 is a coloring for this graph. So you have X, Y0 taken out. So this graph does not have this edge. And here you have X, Y1. Don't worry about other things. Say C0 give color beta to this edge. And then I change the graph. You see, the graph becomes that X, Y0 is an edge, but X, Y1 is not. And this edge is also given the color beta. So this is my C1. So this is the only difference between C0 and the C1. So the coloring changed together with the graph. The graph also changed. Is that okay?
Yeah. Thank you.
Yeah, so I mean, it's a little complicated, but you try to run it in your mind. So you can imagine that you take this edge together with this color and move it here. You move this thing here, but after you move it here, this XY1 is not an edge anymore. You take it out. So eventually you have this graph. So this graph XYK is not an edge. So we are talking about G minus XYK. And you define this coloring CK. So the way you define CK is you move all these edges like a fan to another edge. And the reason you can do it is because of how you find this sequence. So for each yi, this color exactly is missed by yi minus 1. So you put it there, you don't create contradiction with the proper coloring. So you have this. So now suppose in the final picture, we suppose that the vertex yk, it misses some color beta in the final coloring ck. Okay, so let's continue. If x also, so this is some argument similar to previous one. So if x also misses beta, then we are done. We put beta to we assign beta to this edge, xyk, and we get back to G. So this is proper coloring, and get a proper coloring for G. The point is we never introduce new colors. So total number of colors we used is not more than delta plus 1. So with at the most delta plus 1 colors. Okay. So this is a simple case. So another case that x does not miss beta. Okay. So x. Okay, this is the kind of case A. Case A. A simple case. So this kind of argument we use many times. Similar arguments. Case B is that x does not miss beta. But we know that beta is not appearing here. So if some edge is appearing here, it contradicts our choice of the sequence. We can continue to define yk plus 1. Okay? So no edge here is given color beta. So then, in this case, x does not miss beta means that some edge incidental to x was assigned with color beta. So it does not miss beta. It means the following. We have more pictures to draw. It means that some edge here we have beta. Okay, so let's draw one more picture, another picture. So it will be something like this. So this is my yk, and here is my x. And earlier sometime you have yi minus 1. I put I minus 1 on purpose. Okay, so this guy is assigned with color beta. And the yk misses beta. This is our assumption. Yk has no beta. X has beta. Okay. Now we choose any alpha which is missed by X. Again, actually, at this point, you can assume that no color is missed by both vertices. Otherwise, you can put that color there. So using the arguments we used many times. So you choose any color alpha which is missed by X. Then by a similar argument, we know that YK does not miss alpha. So, okay. So we are in the situation of the claim. Okay. So this vertex miss beta, but it does not miss alpha. And this vertex, it misses alpha, but does not miss beta. And we consider, by the claim, we will consider the maximum alpha beta alternating path. Starting from X, because we already have one edge here. So this path must be something like this. So it must be some alpha here, and it goes on and come back here. We call this path P. Okay, so this path is called P. Right. Okay. Good. So this is like the local picture in the color in CK. But okay, we have to come back to CI. You see, CK minus 1 until CI. We have to look at the moment that this edge was moved here. Okay, so we need to look at the color in CI minus 1 and how the definition how CI minus 1 becomes CI. So let's look at CI minus 1. So in comparison here, this is the edge at the point CI minus 1 you have, this is YI. And here, X, Y, I minus 1 has no edge. This is CI minus 1. And the beta is moved here. You see? So remember, the definition of CI minus 1 to CI, we move this edge to this edge. And maybe this is our YK here. And so on. Here you have Y0. You see? So this is the picture for the color in CI minus 1. So the next step, so if you remember our definition, the next step, when we try to obtain CI, we move this here and result in this picture. So this edge is colored beta because it must be in color CI minus 1. It was colored for the edge XYI. So this is the picture for CI minus 1. Okay, so now if you look at this picture, is CI minus 1, which is a coloring for the graph G minus XYI minus 1. Okay, so you have to write every coloring, and remember it's a coloring for which graph. So it's graph changed. If you look at this, you see x misses alpha. X always miss something, doesn't change. Okay, you only change the position. So if x misses alpha, it misses alpha for all the coloring, all the graphs. And in this case, yi minus 1 misses beta. Right? I minus 1 misses beta. yi minus 1 misses beta because you move beta away. So here, yi minus 1 has a color beta. But here for sure, yi minus 1 misses beta. So use the claim for this graph. For G minus X, Y, I minus 1. And the coloring C, I minus 1. So let's repeat what's, so the maximum alpha, beta alternating path starting from yi minus 1. Now, the non-edge is this non-edge, okay? Starting from yi minus 1 must end at x. But here is a contradiction. Okay, let me explain why. It's very subtle. So it cannot, because it must be something like you start from alpha here, and you end into x using some beta. But we know that. So suppose you see, but we know that this, if you look at this path P, it follows this path P until alpha. So this is alpha, you see. So let's draw this P again. So here is alpha. You start from beta here, and here you have alpha, and so on. And this P and at the point yk. So you move everything here. You look clearly that here you see this is alpha, this is alpha. You didn't change anything, and you have this, and you end at the vertex yk. Okay, but ykx, so the final, this is alpha. Ykx is not beta. Here is not beta. So this path P prime cannot end at x. When it arrives, when this P prime, when it follows the original P and arrives at yk, it stops. So it contradicts our claim. Our claim is that, okay, in this case, it must arrive at x. So this is a contradiction. Okay, it's really subtle. So I suggest you try to look for the Wikipedia page and read it. So I try to rewrite this and added some pictures in my notes. So the thing is, it's only several paragraphs, the proof. But when you expand it and really understand it, it's complicated than it seems. So because if you read the Wikipedia page, there is no picture, and it's not very long. So maybe after maybe later when I finish the example, I will show you that page. Okay. So this is the whole proof. So there are several steps. We start by proving a claim, which is related to the claim is related to the minimal example, the part of the induction. And in step 1, we constructed this Weising fence. And in step 2, we construct a sequence of colorings and moving all these graphs. And in the final step, we play with this claim and reach a contradiction. Okay, so I hope that's it. So it's not very easy. So in the final part, let me see an example. So the example is the following. So let's clear our mind. So for complete graphs Kn, what happens is that if n is odd, then the chromatic index of Kn is actually n. Okay, if n is even, then the chromatic index of Kn is n minus 1. So n minus 1 is the maximum degree. So every vertex has degree n minus 1. And this is maximum degree minus plus 1. Okay, so the example is even the example is not so easy. So let me see. It's very clever, but so let me look at you see K2. So one I. Okay, so maximum degree is so what's the chromatic index of K2? It's 1. Okay, so it equals dot of. So it's even. Okay, it's equals so it's even, and maybe I got it confused. This is equal. Yeah, okay, it's equals delta of G, right? Yeah. N is even, and n minus 1 is 1. Okay. So this is kind of the case 0. So case 1 is odd. So let's draw a regular. So we already know that if n is odd. So we leave so okay. We want to prove that we want to prove that the chromatic index of Kn is n. Okay. So because we know that it's either n minus 1 or n, so we need to show that we need to prove that this guy cannot be n minus 1. And I don't want to show this, so leave this as an exercise. It's not it can be done. It can be done by counting edges. It's very interesting. Okay, it's not very difficult. Okay, so in fact, I want to show case 2, n is even. Okay, so it's an interesting proof. So let's take the goal is I want to prove that when n is even, the chromatic index is n minus 1. It equals the maximum degree of Kn. It's a stronger result than Weising, because Weising says that it's at most n. So to prove this, I take V0, and then this is my V0, and I look at the remaining copy of Kn minus 1. Okay, so I know that here, so here is a copy of n minus 1. I know that here I can, in this n minus 1, I can color edges using n-1 colors. Okay, because the chromatic number of Kn-1 is at most n-1. Okay, but I want to show that for Kn also, I don't need to introduce more colors. I use n-1 colors, it's enough. And this is not very difficult because look, in Kn-1 for any vertex V, its neighbor, so degree of V is n-2. So among these n-1 colors, I used, so using this coloring for this copy of Kn-1, I only used the n-2 colors. And then I just assign this edge with the missing color. So let me write the final words. So since, so maybe I can color, I can define a coloring C of this Kn-1, okay, using at most colors, okay. So since for V in Kn-1, degree of V is n-2. So in this coloring C, V misses some color, for example, beta in this n-1 colors. So we assign this color, we assign beta to V0V. Okay? So using this kind of coloring, we can conclude that you can use n-1 colors to give a proper coloring to Kn when n is even. Okay, so okay, so maybe I should introduce this earlier, because after a difficult proof, this is a bit difficult for you to concentrate. But this is an example because it's natural to look at complete graphs. And even for complete graphs, the point is, even for complete graphs, you see two different situations that delta G and delta G plus 1 as a chromatic index. All right, so that's all. Okay, so let me stop the recording.